times the square root of s of x over c of x plus d of x times the square root of s of x dx, or a of x dx over b of x square root of s of x, where a, b, c and d of x are polynomials in x and s of x is a polynomial of degree 3 or 4. More simply stated, an integral of the form r of w and x dx, where r is a rational function of w and x, and w2 a cubic or quartic polynomial in x, and r contains at least one odd power of w, and w2 has no repeated factors. There are three standard types of elliptic integrals. The elliptic integrals of the first, second and third kind, where f of k phi is the first kind, e of k phi is the second kind, and pi of n k phi is the third kind, where k is the elliptic modulus and phi is the Jacobian amplitude, and n is a constant known as the elliptic characteristics. These integrals are known as Lagrange elliptic integrals or Lagrange Jacobian elliptic integrals. If phi is pi over 2, then the integrals are called complete elliptic integrals and are denoted by k of k, e of k, and pi of nk.
Now that we've introduced elliptic integrals, let's explain where they came from. Elliptic integrals have actually existed for hundreds of years and were previously known as elliptic functions, before the term was changed to elliptic integrals, while elliptic functions are now used for a different idea but are still closely tied to the concept of elliptic integrals. The first studies into elliptic integrals can be tied to integral addition theorem, where in 1655 an English mathematician by the name of John Wallis began the study of elliptic integrals by examining the arc length of ellipses. This is the earliest known study of elliptic integrals. Moving down the timeline, we have Swiss mathematician Jacob Bernoulli, who furthered the theory of elliptic integrals in both 1679 and 1694. The first contribution in 1679 was when he discovered an example of an elliptic integral while trying to find the arc length of a spiral. The next contribution in 1694 was when he discovered a new elliptic integral, which is now known as the Lemniscate integral. The integral gets its name from when Bernoulli examined the shape of an elastic rod when compressed at its end. During the study, he introduced a Lemniscate curve to the curve of the elastic rod he examined and proved that the resulting integral satisfied the definition of an elliptic integral. The next mathematician to make a large contribution to the study of elliptic integrals was French mathematician Adrien-Marie Legendre. In his studies, Legendre showed that the integration of a specific elliptic integral can be reduced to the integration of three different integrals. He named these integrals the elliptic integrals of the first, second, and third kind. However, our modern-day understanding of elliptic integrals and functions actually come from two other mathematicians who both independently discovered a new approach to getting elliptic functions from elliptic integrals. These mathematicians were Niels Henrik Abel, a Norwegian mathematician, and Carl Gustav Jacob Jacobi, a German mathematician. Their discovery was the inversion of elliptic integrals.
The solutions to many problems in physics, chemistry, and mathematics involve the use of integrals. They have not only been used in simple calculations such as area and volume, but also complex differential equations and complicated calculations. In the case of more difficult definite integrals, they can be altered to a different form to be solved. One form is elliptic integrals. Elliptic integrals are well known in solutions to finding simple pendulum, a beam under compression, to calculate the potentials of uniform circular disks, and to determine electromagnetic fields of circular currents. For this task, two applications of elliptic integrals will be briefly explored below. The circumference or arc length of an ellipse. Unlike the circumference of a circle, calculating the circumference of an ellipse is a complex mathematical problem due to its inability to be solved using elementary functions. This means that linear combinations of trigonometric, exponential, or logarithmic functions alone cannot be used to solve this type of problem. Thus, elliptic integrals of the first kind are introduced as a means to compute the circumference or arc length of an ellipse. Similarly, the position of a pendulum can be determined using a trigonometric function as a function of time for small angle oscillations where m is equal to the mass of the pendulum, r is equal to the length of the pendulum, g is equal to acceleration of gravity, and alpha is the starting angle as illustrated in the figure below. But to determine the entire solution for arbitrarily large displacement or full pendulum path requires the use of elliptic integrals. Evidently, elliptic integrals occur in a wide variety of situations in the physics and mathematics world.
The computation of the arc length of a selected ellipse is best achieved by calculating all the little arc lengths of the curve. This implies that the arc length s of a curve C is given by s is the integral over the curve of ds. Considering we are looking at an ellipse with major axis A of 5 and minor axis B of 3, we can use the equation for the ellipse alongside the eccentricity, which is a number that characterizes the ellipse, to help parameterize the ellipse and give s is equal to a cosine theta and y is equal to b sine theta alongside both dx and dy. In doing so, we obtain that ds squared is equal to dx squared plus dy squared, which works out to the square root of a squared sine squared theta plus b squared cosine squared theta times d theta when subbing in dx and dy. With this, we would like to manipulate it such that the eccentricity is within the formula. This can be done by factoring out an a while writing in terms of cosine, giving us a result of ds equals a times the square root of 1 minus cosine squared theta instead of sine squared theta, plus b over a squared times cosine squared theta. As we are looking for a 1 minus b over a squared, we can multiply by cosine squared theta to obtain it in the solution. We then replace this within our solution with eccentricity e to get the formula a times the square root of 1 minus e squared times cosine squared theta, all multiplied by d. This formula can be inputted into x, which will be in the terms of the parameter theta goes from 0 to 2 pi. In doing so, a comes out of the integral and the square root is shifted to the power of a half, meaning we are left with our elliptic integral of a times the integral of 1 minus e squared cosine squared theta, all to the power of a half times d theta. The computation of this elliptic integral when subbing in the values of a and e for our selected ellipse respectively provides a total arc length of 25.5.
Okay. That's
Okay, so that's your conclusion?
yeah.
Alright, thank you very much.